Hello everyone, welcome back to Alkaline Hydroxide 784, and today it is a physics series and today we'll be doing superposition. Unlike my other videos in the mathematics and physics series, I am going to be doing the recording of the audio and the video at the exact same time. Let's see how this goes. If it is actually more effective than doing it separately, I might do that for other videos too. But I'm just gonna do it today because I don't have time. That's the reason why I'm doing that. Okay, so yeah, let's just start. Oh wait, I forgot to open the PDF I needed to open. Let me just do that real quick. Okay, so superposition is finally the chapter where you get to see the string and the pipe stuff. So yeah, we'll finally get to that thing which I was talking about 2 episodes ago. How brilliant of me. And of course, superposition is also one of the harder topics because it has a lot of stuff to remember, a lot of things to talk about, a lot of stuff that you need to know about. And it may be a bit overwhelming at times, but I think it will still work. Kind of. Okay, so for superposition, once again, I'm just going to follow the learning outcomes and let's see how that goes, I suppose. Haha. Okay, so the first learning outcome is about the principle of superposition in simple applications. So what is the principle of superposition? Actually, I don't remember. Okay, I'm pretty sure it was something to do with the fact that if two waves going in opposite directions interact with each other, they will produce some kind of superposition in a sense. Like they will interfere with each other either constructively or destructively and produce a resultant wave. So that's the idea of superposition. If you want to know what's the difference between superposition and superimposition, is that superposition leads to the two things combining, versus superimposition is when you put one image and then you just put another image on top of it. And it doesn't like merge together, it just looks like two layers. You know what I mean? There's a difference. So that this is superposition. No, this is going this way, then this is going that way or whatever other direction, and then it leads to a resultant wave, you know. Yeah. Uh, yeah, you can just write this in words and you'll be fine. So, how do you use this in certain applications? Well, I can use it to superpose certain light waves or sound waves or any kind of waves to create certain effects or to achieve certain goals and purposes. So like for example, if you want to focus your light into a certain point, then you can use two sources of light and then they will focus on the center. Or if you want to use like, I don't know, or for cameras as well, when you are looking at two distinct objects, you want to see how far they can be before they're too blur or before it's not working, then there'll be another thing in this chapter which is useful for you called the Rayleigh criteria. I don't even know how to say his name, but sorry. But you get the idea. There's many places where you can use superposition, so don't don't think of it too lightly, especially since the topic isn't particularly light. So yeah, that's pretty much it. Okay, so the second learning objective is about the terms interference, coherence, phase difference, and path difference. So as I mentioned just now, the principle of superposition states that when two waves in traveling towards each other, you know, meet at a point, they form a resultant wave, I guess. Yeah, so how does this resultant wave come to happen? Like they interfere constructively or destructively to form the wave. So interference is what they refer to when the two waves touch and then they interact with each other, they merge into each other. That's interference. And in interference, you can have constructive and destructive interference. So constructive interference is when um, constructive. Okay, constructive interference is when you have like this wave is also going up and this wave is also going up, and therefore the amplitude of the resultant wave is double that. It's like the summation of these two. So the amplitudes of the waves add up. And destructive is the opposite of it, I suppose, because it's what happens when you have one this way and then there's one this way, and therefore the resultant wave will just be like a smaller version of this. So this one minus this one. Or if they're equal, it will just be a flat line, like there's no amplitude. And that's why you get your, that's why your stationary waves has a, that's the moment where it can be flat as well. So it goes up, it goes up and then flat, then goes down, and it just does that really quickly. So yeah, that's interference. So the next one is coherence. So what is the meaning of coherence? Well, if you have two coherent waves, that's how you usually use the word, like two coherent waves. It usually means that the waves are of the same frequency and the phase difference is constant throughout. The phase difference is constant, and therefore the frequency is constant, so the waves are coherent. So let's say if you were to translate them, you can technically fit them on top of each other. Save the amplitude. Amplitude might be different, but the waves will still align with each other in a sense if you were to translate them. Of course, in reality, they may not be exactly like matched to each other, but more of having a phase difference of maybe half a wave or something like that. So that's what it means by coherent waves. And the reason why coherence is important is because coherence helps you observe more observable diffraction and more observable superposition of the waves. And that's why it is very helpful to have coherent waves in superposition. And so what is the phase difference? I think we already covered this last time. It is like, you have two waves, one is like this and then one is like this. So if you see the difference between the two crests, of course you have to have the same frequency, otherwise it wouldn't make sense. So you compare the two crests and that's the phase difference. Like that's the fraction of the wave that is, it's translated by to get the other wave. And the path difference would be the absolute value of the wave going from one spot to another. But this is actually different from phase difference because it is more of the distance that the wave has traveled. So let's say we have 2 points over here and the waves travel this way. So let's say this is 3 and this is 2 meters. So the path difference is actually about 1 meter, and you can represent it in terms of wavelengths. Depending on how long the wavelength is, you can divide 1 meter by the length of the wavelength, and you can say this many wavelengths is the path difference. So that's the idea of phase difference and path difference. So the next learning outcome is about experiments which demonstrate stationary waves, which is where we finally get to talk about our favorite thing, the string and the pipe. I mean, yeah. Sure. Of course, microwaves are also mentioned here. By microwave, yes, it is like the waves you get in your microwave oven. It is really the same thing. But I guess you don't need to really know too much about it. You just need to take note of it like a normal wave. So a microwave would be, I'm not sure what they actually mean by experiment using microwaves, because I'm not sure they're saying, oh, the microwave in the microwave oven also interact to form a stationary wave, which in turn provides heat to the object. I don't know. I'm not exactly sure. But if they ask a question about it, just know that, yeah, just treat it like a normal wave. So let's look at the stuff that we can actually visualize, which is the string and the air column. So for the string, you would have like a you first have like this somewhat taut string, attached at 2 points. So these points are stationary here. And since these points would never move up or down, they are called nodes. So they will forever be in this line here, this particular axis. And these point that, and there'll be many nodes on it depending on which stationary wave you produce, like which harmonic or which overtone that you try to recreate using the string. So if you're looking at the very first one, obviously these are the only two nodes. And in the middle there is an antinode. So the node will be the N and antinode is the A. If you were to look at 2, the second one, then you would be doing something like this halfway through, and it forms a wave like this, and this will be another node, and these two will be antinodes. So that's just the general idea of how it works. And as you can see, for the string, you must make sure that there is one full hump, like some whole number of humps or crests or throws or whatever you call them along the length of the string. You cannot have something that is like, this is a string, and then this is what you get. You cannot do that. It doesn't work with a string. So for a string, it must always be like this or this for it to be counted as a stationary wave. And for the hump, you can, the crest in this scenario, you can also imagine that it will eventually go back down here, and this will be the throw. So this is a stationary wave. It will always be going up and down and up and down. So why does this stationary wave actually form? Well, we haven't really gone into that part yet, right? We were just harping on the frequency and the velocity and everything. So basically what happens is, if you vibrate one end here, then the string will start, okay, let's just imagine this in like super slow motion. So you first vibrate here, and then the string will start like, forming a wave that goes this way. And once it reaches this point, what does it do? It has to return back, right? So, and as it returns back, it will be doing this, right? Right? In a way. So as it returns back, it kind of flips over and then goes the other way around. So at any point in time, the stationary wave is either entirely stationary, like in this one point, or it's at the maximum. So it's either it doesn't really, like, it automatically does this. It superimposes on itself, basically. The reflected wave will superpose onto the incoming wave, and that creates a stationary wave which just alternates between these two states. So yeah, so as the wave continues to move, as this, let's say this point comes here eventually. So at that point, okay, let's say, okay, I'll just draw the ending part lah. So this is the, okay, so this is the ending part. And since this point here would correspond to, like, imagine this part has already gone through, the wave here has already gone through, and it would correspond to a point around here, and eventually it forms like a stationary wave. They just keep superposing to form this kind of a wave. So that's how it kind of works. Like, just imagine it visually and I think you'll get it. So let's go through the frequency and the velocity, and that's what I'm good at. So yeah, I'm just gonna go through that while we are at it. So if you imagine this to be of length L, if for the first one you would imagine that the wavelength is actually two of this, right? Because one wave is one of this and one of this. So one crest and one throw. So this is actually, L is actually half a wavelength. So the wavelength will be 2L, and the frequency is, the velocity of the wave and the frequency of the wave is now like the variable here. Like, one of them will affect the other. So if we are looking at the frequency, we'll use the velocity as the variable here, because velocity is frequency times wavelength. So in this scenario, frequency will be V over 2L. So for the second one, which would have one full wavelength within the L, therefore it is L. So, then the frequency will then be V over L. Then for the third one, you would get 3 hums, so it will be like 1, 2, 3. And this is 1.5 wavelengths in a L in a sense. So the wavelength is L divided by 3 over 2, which then means 2L over 3. And therefore you get V over 3V over 2L, kind of. So from this, you don't really see much of a trend yet, right? Because this thing just looks a bit weird, this looks like an anomaly. This one got 2L, this one got 2L, but where's the 2L here? I would like to, bring you to attention that the second one, since it's an even number, that's why you don't notice it. So in reality, it is, in fact, lambda is like 2L divided by 2, technically. So this is 2L divided by 1, this is 2L divided by 2, this is 2L divided by 3. So, imagine it like that. And so on and so forth. It'll be 2L divided by 4, 2L divided by 5, and so on and so forth. And likewise, this was actually V over 2L. And this is 2V over 2L, so the 2 cancels out. This is 3V over 2L, then 4V over 2L, then 5V over 2L, and so on and so forth. So for the nth harmonic, I believe, or is it overtone, I'm not sure. So the nth one, you will get 2L over n here, and you will get nV over 2L. So yeah, it works. This is how it is done for the string. So if we move on to the pipe, you will have something like this. And so the pipe, we have two different scenarios, the open pipe and the closed pipe. So we'll start with the open pipe because it's quite similar to the string. So in any pipe, the open end will always be the antinode. So in this scenario, you would need to have something that is like this. So this is the node is in the center, and the antinode is at the end. So in this scenario, what exactly is vibrating? It is the air particle, because you're producing a sound, and when a sound is produced, the air particles vibrate to transfer the sound. So yeah, sound needs a medium to pass through. You can't really hear sound in space that much, because space doesn't really have much of matter to pass air through it. So I mean, to pass a sound through it. But light can go through, so yeah. Yeah, okay. So this is an antinode and it's a node. So in this scenario, you might be wondering, how do we go about doing the wavelength thing, and why is it similar to the string? Well, if you think about it, the string was like this, right? It was just one hum. Let's say if you cut this into half, and this is on top, and this is like flipped over and put at the bottom. It's the same thing, right? So this is 1/2 of a wavelength. This is actually 1/2 of a wavelength. If you look at the next one, then it'll be a little bit more clear. This is a full wavelength, in fact. So it's the same thing, the same pattern here. There's no change, really. The only difference is that the antinodes are at the end and the node is in the middle. That's the difference. So this is still the same for the open on both ends kind of pipe. And then we have the closed on one end kind of pipe, and it's only the open ends tend to have antinode, so the closed end will always be a node. So just remember that. So since this is a node and this is antinode, for the very first one, it will actually be something like this, kind of. So this is what it looks like. And the next one that you get will be something that's a bit like this. So in this scenario, what we considered, if this is the L, the length of a pipe, then the wavelength is actually 4L, kind of, because this is only one half of the crest, so you need 4 of this to get a wavelength. And then for this, in this scenario, the second one, you would be seeing that there's one hum and 1.5 hum. So what does that mean? It means that the lambda is divided by 3 over 2. So, yeah. So 2 over 3L. And then the next one will be 1 hum, 2 hum, and then half. So it will be 5 over 2. And so on and so forth. So in this scenario, if, okay, I'm saying 1, 2, 3, but there's also the possibility of saying 1, 3, 5 based on whether you call it a harmonic or an overtone. So please be careful and know which is which. Yeah, so if you're looking at the nth, I believe harmonic, or yeah, nth harmonic, or is it overtone? No, it's not, sorry, overtone is the 1, 2, 3, then harmonic is 1, 3, 5. So if you're looking at n minus 1 overtone, which should be like, yeah, you would then get, let me see, so this is like 2 over 1, but then that's not 4. Wait a minute. I don't know. Okay, so but in this scenario you can see that these are all odd numbers. So if you were to look at it in terms of harmonic, we would say this first harmonic, third harmonic, fifth harmonic. If you're looking at nth harmonic, then we would say 2 over NL. Right. Yeah, 2 over NL, and the velocity accordingly will be based on, sorry, the frequency will be based on your velocity. And yeah, that's pretty much it. I'm pretty sure this was different from the other one. Why does it look too similar? Yeah. Oh, sorry. There's a difference. This is 4. This is actually 3/4 of a wave. I cannot think. Okay. Yeah, this isn't even a full wave yet, right? So it's 3/4 of a wave. So the difference between the completely open pipe and the one end closed pipe is that the completely open pipe is in terms of halves, and the one end closed pipe is in terms of quarters. So you have 4 instead of 2. Cool. I hope that clears it up. Okay, so let's move on. I don't want to spend too much time on this. So before I move on, I would like to say something about the end correction. So end correction is something that happens in the pipes, not for the string, because the string is really limited at the two ends. But here we are depending on the movement of the air, and air isn't gonna be staying at the same point at the same time. What's that sound outside? Why is there a police or ambulance or something? Never mind, hope it's nothing too serious. Okay, so when it comes to air, the air molecules will keep moving here, even if they form a certain antinode or node or whatever it is. They will keep moving and causing certain certain disturbances, like certain variations to the actual length of the wave. So when it comes to the air pipe, you should consider a possible end correction at any open end that you have. So if it's open on both ends, you have 2 end correction. If it's only open on one side, then you have 1 end correction. But for most of the time, you don't need to worry about this in your question. You only need to worry about it if the question explicitly asks you to talk about end correction. So, okay, never mind about that. So when it comes to end correction, you use the letter C to represent your end correction, and for open you use 2C, and for close you use 1C. So you just add that to the L before you do these formulas. So like instead of L, this will be like L plus 2C or L plus C, you know what I mean? Like it'll be something like that, for example. So just be a bit aware of that when you're doing your question. Sometimes they may actually ask you to find out what is the length of the end correction by giving you certain values and also the value of the length of the pipe or something like that. They may ask you to find anything. So, just be prepared for that. Yeah, it's possible. Anyway, it's just a matter of simultaneous equations. It'll be there in no time, no issue. So, the next learning outcome is about uh it's the formation of the stationary wave, which I kind of showed you kind of half-heartedly, but yeah. I'm not sure if you really got it, but let me see if I can show it to you one more time. Okay, so for the stationary wave, we first imagine that it starts from this point, and there's like a reflective point here. So the wave goes up, down, up, down, up, down. Okay, so as you can see, it stops here, right? But you know that it wants to form more of this wave. So this will actually reflect this way, kind of. And it will go back. Kind of like this. So when this happens, the wave will eventually superimpose on itself. Kind of. Superpose on itself. I keep saying superimpose, sorry. So in this scenario, what you will get is that here, for example, since this is actually a node, this is actually at the maximum. I mean, not really maximum, but around here. Okay, wait. Okay, I'll take note of the. Okay, I can't really think. But you get the idea. It forms like that same bump and the stationary flat areas as well. Oh, didn't focus. So like based on where exactly the wave is, it will superimpose on itself. So yeah, so in order to get a perfectly stationary wave, you need to have like a phase difference of about like a phase difference that's like half of the wave, or like that kind of phase difference in order to actually see see a perfect stationary wave. It needs to align properly and give you a nice stationary wave, kind of. So that's why the length of the pipe or the string matters, as well as the frequency. So all of these things need to come together in a perfect sense to give you a good stationary wave. It doesn't work at all frequencies. So yeah, I think you know where the nodes and antinodes are, so it shouldn't be an issue. Let's move on to the next part, which is about diffraction. So what's the meaning of diffraction? Diffraction is the act of like the wave forming a pattern, an interference pattern, when they interact with each other through superposition. So so in diffraction, you can have like one source or two sources, or any number of sources of like waves that form a certain pattern based on how they superimpose or something like that, for example. So that's the idea of diffraction. So the next one is about the experiments which demonstrate diffraction, including the diffraction of water waves with both a wide gap. Okay, so diffraction the one that you're supposed to write about is like diffraction is the interference of, how do I say it? Diffraction is is the act of superposition that occurs when a wave passes through an aperture or around an obstacle. So that's what diffraction is actually. So that's what you need to write about the aperture and the obstacle thing. Okay, how do you actually observe diffraction? Simply by passing a wave through an aperture or an obstacle. So the one that you usually see is the water ripples, the ripple tank thingy. So you can see how the water waves move in the sense. So so for water waves, you usually have like a tank. So this is the top view of the tank, and then you have some kind of thing here that will keep producing waves. So it moves up and down, and from there there'll be water waves that are produced in a sense. So let's say this entire thing moves up and down, up and down. Then there's a little aperture here, and after the water waves will be moving this way, and based on the aperture, you will eventually see some kind of a curvy pattern here because of the fact that this aperture blocks this area and this area, and it forms like a little curvy pattern, and then it goes on and goes, and so like it just forms like a little wave in a sense, a ripple kind of effect. And the difference between the wide and the narrow gap is that when the gap is very wide, the effect is less pronounced, so the wave doesn't look super rounded. But when the gap is super narrow, the wave is pretty round, like it looks very round, even after becoming bigger and bigger in a sense. So that's the difference between the wide and the narrow gap. So the next learning outcome is about two-source interference. Uh, two-source interference is, well, basically your Young's experiment. You can use anything. You can use water waves, you can use sound waves, you can use light waves, you can use microwaves. Actually, microwaves are just light waves that you can't really see, but you know. So water waves would be something that looks like this. So you can have like two sources, two little thingies dipping inside and outside the water, forming two round water waves rippling out like that. And then they can interfere in a certain way. Or if you have like if you have sound, you can have two sound emitting devices that produce sound like this. It looks the same no matter what waves you get. And for light waves, it's the same thing. You just imagine two sources of light. But usually in light waves, you don't need to do the one that emits in all direction, but more like two, like you imagine two light waves this way and this way. Actually, it's still in all direction, but like the idea is that you don't really need to worry about the rest of it. Just worry about this side. And of course, microwaves in the same way. Like you use something that produces microwaves. So how do you do it with light? We will go. You look at it later on. So let's first look at the conditions required to see two-source interference fringes. So of course, when there's two-source interference, these two waves will end up interfering with each other constructively and destructively. So when it interferes constructively, you would realize that like how do you see that it interferes constructively? Well, if you see that there's a certain distance from each of them, the waves need to be, you know, both like this, right? So it doesn't matter how much the phase difference has to be zero, and in that case the path difference has to be you know, if it can't really be half a wavelength, so it must be a whole number of wavelengths. So for constructive, you can, if the phase difference is if the phase difference is zero, then the path difference will be you know, the path difference must be a whole number of wavelengths. But if the phase difference is actually half a wave, like you know, pi or whatever, half a wavelength, then the path difference cannot be a whole number of wavelengths anymore, right? It must be, you know, n.5 kind of wavelength kind of thing. Of course, that's not how you look at it, so instead write n over 2. So yeah, pi. And conversely, for destructive interference, if your phase difference is 0 between the two sources, then the path difference to get destructive interference is half a wavelength, or like NO2, any half 0.5 kind of wavelengths. Okay, so for destructive interference, if the two sources have a phase difference of pi, then you would need a whole number of wavelengths in order to get destructive interference. Okay, so let's move on to the next learning outcome. So now that we know that there's all these, like this, how constructive and destructive interference works in two source interference, then you need to see what are the conditions that you need in order to actually get this kind of a interference pattern. So of course it's quite useful if it's quite important for the two sources to be having the same frequency, and if you want your interference pattern to be more visible, it will also be useful for them to have about the same amplitude, so that when constructive interference occurs it will be like maximum amplitude, and when destructive interference occurs it will be as minimum amplitude as possible. So that will be the kind of conditions that you require. So you need coherent waves, you need to have about the same frequency, and you need to have about the same amplitude. So the next learning point is about the double slit interference and all the equations that we require in order to solve double slit interference problems in a sense. So if we go to Young's experiment, if we were to visualize that in a way, we would have usually how it's done is that first a source is sent into into two slits basically. So the source of light will be here, and this will produce two coherent sources of light because of the diffraction of this single source of light. So the distance between the two apertures here will be A, and then you have the distance between the slits and the point where you see the pattern like a wall or something. That will be represented by a big D, and from here you need to come up with an equation, right? So the equation will then be determined by how the two sources interfere and eventually reach the wall on the other side. So when you have two source interference, you will be getting maximum amplitude at the middle. So you will be having maximum amplitude at the middle, and then it'll create many minimas and maximas afterwards. So from here, you would need to know there's one thing that would be helpful to know, which is the distance of in between two maximas. Here it would be x. So the equation connecting all three of them would be lambda equals to ax over d. So how does this come to play in a sense? If you imagine the center point here, and you have you imagine a light wave from here and a light wave from here forming a certain maxima at a certain point. There's going to be an angle theta here, and if you were to magnify that into a greater diagram in a sense, you can do some trigonometry. And for the since these 2 points will have a phase difference of 0, you would need to look at each of the wavelength in the sense. So for constructive interference, you'll be having the difference of either no wavelengths or one wavelength in a sense. So actually it's not very important to really know how the equation is derived in for A levels, but if you want it, I can do a separate video on that because I can't think right now. But in this scenario, you will be getting something that will eventually give you this equation. And for this to be true, you would need to have the wavelength of the light be much smaller than the slit separation, which should be smaller than the distance here, the big D. And this equation will serve you well for any question that asks you to, you know, that ask about the double slit interference or anything related to that. And for the single slit diffraction, which is quite different from double slit diffraction in the sense, you imagine that instead of one source being split into two, you just have one source going through one single slit here. And that itself will produce a diffraction pattern. And it's quite different because of the fact that only one source is producing the pattern without any interference with a secondary source. And in this scenario, you'll be getting a different equation in the sense, which for that we would need to write down all the variables again. So this will be D, and the width of this in A levels it seems to be represented with a B. And if we have the the interference pattern, the width of the center, like the length of the center crest, basically the central maximum, will be represented with Y. And yeah, your resultant equation would be something that is equivalent to sine theta equals to lambda over B. So in other words, B sine theta is equals to n lambda based on which n you're looking at. So this theta is actually the angle from the center point until the maxima, and it's the angle between the center and the, sorry, not maxima, minima, the first minima. And you can use this to find each and every minima here. As for double slit interference, the equation would actually be more of A sine theta equals to m lambda or n lambda. In this scenario, you're looking at the angle from the center to the maximas rather than the minimas. So that's a difference between double and single slit, and you need to take note of these differences. So yeah, so how does this single source create this pattern? There's actually a principle called Wiggins Principle. Actually, I don't know how to pronounce that, but you get the idea. And it basically states that when you have a single source, that single wavefront of the source will have multiple points on it which act like little wavelets. So that overall wavefront is the summation of the multiple wavefronts along the entire wavefront in the sense. And when it passes through an aperture, some of the wavefronts are bound to be, blocked in the sense. So this is actually more related to diffraction. So this is how diffraction works. And the wavefront that pass through will still be here, but there'll be more. But since this wavefront is actually curved, right? The new point where the wavefront can form is this way. So it ends up forming like a curve, and since these points move towards the sides, it forms a bigger and bigger curve as the wave progresses. And since this itself has many little points, many little waves, in a single slit you can imagine it as two sources based on where you take it. Like you can take one from here and one from here, and they will produce their own curve, their own curved waves in a sense, which can interfere with each other. And that's why it kind of works. So is there any relationship between the double source and single source diffraction patterns or interference patterns. Well, there is actually, because in a single source you're imagining two sources based on these distance between, like the half, each half of that aperture. But in a double slit we are looking at two separate apertures. So what happens is that if you were to draw the single slit interference pattern and then draw the double slit interference pattern, it will actually fit in. The double slit one will fit inside the single slit one, but there will be certain points in which the maxima of the double slit will be coinciding with the minima here, and therefore there will be no observed pattern on the double slit interference as well. So for example, let's say if this is 1, 2, and this is supposed to be 3, but the third one is blocked by this particular diffraction envelope of the single slit diffraction in a sense. So the next thing is to apply the double slit diffraction into a more, into a bigger context, or into a context with more slits, which is in a diffraction grating. So a diffraction grating is something that helps you to diffract light, and instead of just two slits, it has multiple, like many of them. You can have like 500, 1000, I don't know, it depends on the number that's written on the diffraction grating, or whatever number you get in your question. So they may either give you the number of slits, or they may give you the distance between each slit. So you can use that to figure out what is the actual d in the sense. So instead of using a, they use d sine theta equals to n lambda. In this scenario, d is actually the distance between each slit in your diffraction grating. So that would either be the length of the grating over the number of slits, or it's already given to you in the sense. So in a diffraction grating, there's an even greater focus because there's multiple slits which can focus light even more. The constructive interference is even greater compared to just two slits in the sense. And that's why you can get a really nice coherent source of light from the diffraction grating in the sense. So you can use this to find the maximums once again, just like the double slit scenario. But in the double slit scenario, you don't really use the a sine theta equals to n lambda, because it's only two slits. So here you can just use this directly. In that one, you can use the lambda equals to ax over d, and that's more useful in that scenario compared to the a sine theta equals to n lambda. But you can still use it, just saying. So yeah, that's how the diffraction grating works. Right, so when you're doing questions like this, you do realize that the angle that you get is actually pretty small. So if you are asked to mathematically derive the equations, draw a nice diagram about it, use the trigonometric identities, and realize that the theta will be somewhat, equal to sine theta and to tangent theta because the angle is very small. So just take note of that when you're doing the derivation, or if you're asked to ever do the derivation. Okay, so the next point is Rayleigh's criterion, which is to see the resolving power of a single aperture. So this is what I was talking about, like the camera or like a telescope or something, and you want to see two objects and see them somewhat clearly, or to see them as distinct objects rather than as one blurred together object. So what is the distance between them that you need before you cannot see them as this? In order for you to actually see them as distinct objects, well, you can imagine it as two waves that go this way, and for the other side, it would be something like this. So the maxima of this particular source will align with the minima of this source. So this is 1 and this is 2. So this must align with this must align with this. And then in this scenario you can see the two sources clearly enough. Of course in reality these are the only ones that will be really have a really high amplitude, and the rest will be quite small, basically very small waves. But the idea is that the maxima here will coincide the minima here, and the maxima here will coincide the minima here, in the sense, and this maxima will coincide with this minima. So that's the idea. And to get this particular distance, as you can see, this is the distance of half a wavelength, kind of. And for that, you would then realize that since this is maxima over minima, you can then use the distance from the central maxima to the first minima, which as you have seen from a single aperture, b sine theta equals to n lambda, right? So since this is the first minima, you can just say it's 1, so it's b sine theta equals to lambda. Then you just say sine theta equals to lambda over b. And because theta is a very small angle, you can just make this theta equals to lambda over b, or approximately equals to lambda over b. And you will then get your Rayleigh's criterion. So you can use this to find the resolving power of a single aperture, to know the distance that you require before the objects, in order to see the object clearly. And if you're having a round aperture or something, it's 1.22 or something like that. So I just remember that if you have that in your note, just remember it, and it might be quite useful. Okay, so for the last learning outcome is about using diffraction grating to determine the wavelength of light. Okay, so sorry for jumping back to diffraction gratings. Or I didn't show you this diagram clearly, sorry. Let me just show it to you while I talk. So when you're using a diffraction grating with normal light, like the light you just get from the sunlight, you will actually get a rainbow, because the different wavelengths of light are diffracted to different extents. So it kind of separates them out into the different colors. So you can then use, if you're using monochromatic light, you can then use this idea of the distance between each maxima or minima, in order to find out what wavelength of light that is. So you just need to use the equation from earlier and just apply it to that scenario. And if you are supposed to draw the pathway of undiffracted light through a diffraction grating, and the light isn't monochromatic, then you must draw the more than one wave pattern, or at least show where the first maxima ends and where the second maxima starts, in a sense, because certain colors first maxima will coincide with certain other colors second maxima. So the distance is that great. You can see the overlap in the rainbow. So yeah, I think we're done. I'm kind of I think I talked for very long, and my phone also ran out of storage like 2-3 times. So yeah, I hope you found whatever I said reasonably understandable. And if you found this video useful, you can press the like button and subscribe. And if you have any questions, please ask me in the comments below, or if you want me to cover something in greater detail, you can give me a comment, or you can just PM me in Reddit. So yeah, with that, I would like to say thank you and bye.